I'm sorry?
I got a problem. I
Uh,
got to review. I don't understand it.
it's from chapter 6.
Yes.
Okay, how about I'm recording this lecture. After we finish recording, I'll do that. Okay? All right, so we are going to do work and energy in this chapter. Okay? So the title is Work and Kinetic Energy. Okay? Um, Again, these are some of the topics we'll cover. We'll define kinetic energy. We'll see what we mean by work. Okay? And when you account for all forces doing work, what you learn is when you do work, you change the kinetic energy of the object. Okay? And then we'll see how you can calculate the work done by a variable force. Okay. All right. So this guy is pushing this lawnmower. What he's doing is he's transferring, okay, so this lawnmower was at rest, and then he starts pushing it, and what he's doing is he's transferring some energy from him to the lawnmower. Okay? And he transferred energy from him to the lawnmower by doing work on the lawnmower. Okay? So energy can be transferred to an object by doing work on the object. Okay? And you guys know the conservation of energy principle. All you've done is moved energy from here to there. The total energy of the universe has not changed. Okay? And the transfer of energy happened, we are doing work. Okay? So if you do 100 joules of work on an object, 100 joules of energy is transferred to the object. So if you did 100 joules of work on this object, you've transferred 100 joules from here to there. That's what the statement is. Okay? Okay, so to do work, one needs energy. Yeah. So, I mean, we have to do work in the world, and so we're constantly looking for sources of energy, and we'll talk about that as well. Okay? So, as an aside, we'll discuss where the world gets its energy from, and the consequences of these choices. Okay? So, anyway, that's a little extra stuff, so we'll do that. Okay. Energy is a scalar quantity associated with the state of the system. Okay, so energy is a scalar quantity. Okay, so and the state of the system tells you it has a certain amount of energy, which is just a number. That's what a scalar quantity means. Okay, so for instance, the gas in this room has a certain amount of energy, and that's specified by a number. You know. Energy can be transformed from one type to another. What does that mean? So, yep. So you have various forms of energy: heat, kinetic energy, potential energy, electromagnetic energy, chemical energy, nuclear energy. So you can transform it from one form to another form. Okay? Any form to any other form. It can be transferred from one object to another. Okay, so you can transform energy from one type to another and transfer it from one object to another. You already saw that. You transferred energy from this object to that object. Okay? And in that transfer, you also transformed it. This person had chemical energy stored in them. And you transformed that to mechanical energy. Okay? Now, you learn that this transformation need not be 100% efficient. So, for instance, this chemical energy is about 20%, you can transfer it's 20% efficient. Yeah. So, when you run, for instance, yeah, if you use 100 joules of energy in ATP, you're converting 20 joules into motion. What happened to the other 80 joules? Heat. Okay. All right. So energy cannot be created or destroyed, so the total energy of the universe is conserved. Okay. All right, so here are various devices. Okay. So, for instance, an electrical, so these are various transformers we use in our life. So, this device, a light bulb, can convert electrical energy to radiant energy, electromagnetic energy. Okay. A heat engine, so your car, for instance, can convert the energy in the gasoline into mechanical energy. Okay, so it burns the gasoline, produces heat, and converts some of that to mechanical energy. Okay, so your car, for instance, is 20% efficient, just like he is. Okay? And 20% of that heat is converted to mechanical energy, and the other 80% remains heat. Okay, plants convert electromagnetic energy via photosynthesis to chemical energy. Okay, and so on. So here are various transforming devices in our lives. You all know kinetic energy. Kinetic energy is the energy associated with the motion of an object. Okay, so when an object is moving, it has kinetic energy, and kinetic energy is the kinetic energy of an object is given by 1/2 mv squared. Yeah. It's also can be written in terms of the momentum. Okay, so the linear momentum of an object, which is a vector quantity, is its mass times its velocity. Okay, and you take p square as p dotted with itself. Okay, so kinetic energy can also be written as p squared divided by 2m. Right. Anyway, so it's the energy associated with the motion of the object. All right, now we'll, so we learned that you need energy to do work, okay? And now we'll see how you do work, okay? And the formula, the technical definition of work, okay? So let's say this person is pushing this object. The force he's applying is in this direction, okay? And the object is moving in that direction. Okay, so this is the force he's applying, and that's the displacement of the object. The work he's done on this object is given by this dot product. Work done is force dotted with displacement. Okay. Now you know how to take the dot product, but essentially this is a multiplication. Force is measured in newtons, displacement in meters. Okay, Newton meters are the units for work. Okay. And this is given a special name called the joule. Yep. So the SI units for work are the joule. Yep. Anyway, so the work done by a force that's constant, so this force is constant during that displacement. Yep. So the work done by a constant force is given by the dot product of the force and the displacement. Here the displacement I've denoted it by S. Yep. So it's F times S times cosine of the angle between them. Again, that's in here it's theta, but here I've written phi. All right, so I'll write it again. So let's say there's the force, there's the displacement, phi. Yeah. So work done is F S cosine phi. All right, now this is the magnitude of the force. This is the magnitude of the displacement. Okay, the magnitude of the force, it's always positive. Magnitude of the displacement is always positive. How about this guy, cosine phi?
Not always positive.
I'm sorry?
Or always, you may have to add 180 and down.
Okay, so when this is, phi is an acute angle, cosine phi is positive. When phi is 90 degrees, 0. When it's an obtuse angle, it's negative. So work done can be 0, can be positive, 0, or negative. Okay? So When you do positive work on this object, you're increasing its energy. When you do zero work on this object, you're not changing its energy. When you do negative work on the object, you're decreasing its energy. Okay. Do you guys know any situations where you do negative work on an object? Huh?
Breaking your car?
Yeah, breaking your car. Every time you try and stop your car, you have to bleed energy from the car. So you have to do negative work, okay? So when you're braking, you're applying a force in this direction and the displacement of the car is in that direction. That's 180 degrees. Cosine of 180 is -1. Okay? So that's an obtuse angle. All right, so the work done, a scalar quantity. So in this case, here's the force and there's the displacement. And that force was constant, that angle is acute. So in this case, you did positive work on this object. Okay? In this case, there is the force and there was the displacement. That was an obtuse angle. You did negative work. Okay? Here was a force that was applied on this object that was perpendicular to the displacement. You did zero work. This force did zero work. Okay? All right, so we've given you a definition of a force. Okay, now this definition works when the force is constant. Okay, what do we mean by that? See, this object moved from here to there, and the force was always the same. Okay? The force was constant throughout the motion of the object. Okay? So for a constant force, this is how much work this force does on that object. And whatever object it is that you're applying a force. Okay? All right, so as soon as you learn that, so this is the first step. Now we want to go on to a more complicated thing. Okay? All right, so now you're not happy with just that. So what you want to do is, okay, so we're going to move this object from here to there. Okay? And you'll see in a second why I broke this up. Okay. Okay. So now you have ADHD and you're going to change the force you apply. How do we calculate the work now? Well, I gave you this formula when the force is constant, but now I'm making the force change. So how do you do the work? Yep.
Multiply all of them because all of them go into one direction.
So that's what calculus does for you. What calculus tells you is that, well, if the force is changing, break up the thing into small steps. In this small step, the force is constant. That's calculus. Okay? All right, and notice something else. Okay, what is this? This is F cosine theta. This is theta. F cosine theta is the component of the force in the direction of the work, in the direction of displacement. Okay, so it is Fxi, so I'm going to write the x component that way. Dxi. Dxi is the small displacement. Okay, so if your force is changing, at each step calculate the x component of the force and multiply it by that small step, and then add up all the pieces of work over all the steps. Did you guys understand that? Yeah. So you know how to calculate the work done for a constant force. So if the force is changing, just break up your displacement into small steps. In each little small step, the force is constant. Okay? And calculate the work done. Okay, so let me clean this up. This small step is dxi. And what I'm doing is, this is the x component of the force at xi. Okay? So there's the work done in that step. And then you add up all the work done. That'll give you the total work done. And some of you probably already have done integrals. In the limit dxi going to 0, this sum is just an integral. Okay. What is this guy? This is the x component of the force at location x. Okay. And that's what this is. Okay. So what you're plotting is the x component of the force versus the position of the object. Again, this is an object traveling in a straight line. Okay. So this force can be changing. That's the force, and this is the x component of the force at location x. That's what's plotted. Okay. And so for us, okay, so this is x and that's dx, and this is at that location, that's the force, and dx is the displacement. Okay, so for that small step, this was the work done, this strip. Okay. And then you add them all up, and that's the area under that curve, which is that integral. Okay. So again, let me summarize that again. We talked, okay. So this was the formula for the work done by a force that was constant, and then we used this to get the answer for the work done when the force was changing. All we did was broke this displacement into small displacement where the force is constant, calculated the work done for that small displacement, and summed over all of them, which is the integral. And so that turns out to be the area under the curve. Yep. Yep.
Is it like Riemann sums?
Yep. Mm-hmm. Mm-hmm. Yep. All right. So now we have given meaning to integrals. Okay. So if you're plotting a force as a function of position, the area under the curve is the work done. Okay. So we've given meaning to an integral in this case. Okay. And you guys remember we had given meaning to derivatives in the previous chapter, xt, d, okay. What was dx by dt? I'm sorry? Velocity, okay? And so on, okay. All right, so we now calculated work done by a varying force. Again, in all these cases, the object is traveling in a straight line in one dimension. Okay. Now, what would be the natural extension to that? Are you satisfied with this? No. Okay, what do you want next? Okay, yes, exactly. You want the freedom for the particle to be traveling in any direction. Okay, so you could be traveling in that road. Okay. Now, so we'll do that. So let's get to that, and then we'll come back to these slides. Okay. So the natural extension to that is now, let's have the ability to move in any direction. So an object is moving from A to B along that track. Okay. And, well, again, you know calculus, so what you do is you break this path into small little paths. What are those small little paths? Straight lines? Straight lines. You know how to calculate the work done in a straight line. And so you do that. Okay, so you break that into little straight line stretches. Okay. And the force dotted with that displacement is the work done in that straight line stretch. So this is the work done in that small path. Okay. So there's the force, and there's dr. Okay. So that's the work done during this stretch, and then sum it all up, which is doing an integral. So there's the work done, infinitesimal work done during that stretch. And you sum them all up, and you get the total work done in going from here to there. Okay, and that's a line integral that you will do in Calc 2 or 3. Okay? All right, so what you learn is, so here's a curve that you can parameterize. So, for instance, we can say, what is this saying? That's the XYZ coordinate of the object at these times, for instance. Okay? And the force will be a function of that. So I will just do this guy, this one integral. Okay? And again, you'll learn all of this in your xt, yt, zt. Okay, what does this mean? This is the x component of the force at this location. X component of the force at that location. Okay, and you were at that location at that time. Okay, and what is dx going to be? So dx is going to be is equal to dx by dt dt. So dx by dt dt. Okay. So this integral is a one-dimensional integral. So we've turned it into an integral over t. Okay? And you can do the same thing for that and for that. So ultimately, a line integral is ultimately a one integral in one variable. So that's what you're going to convert it to. All right, but anyway, you'll see that. Okay. So for now, what we want to be happy with is the following. Okay, so let me summarize what we have learned. So if an object moves in a straight line, if the force is constant, then the work done is F dot S. You're moving in a straight line, and the force is changing. What you do is you take the x component of the force at location x. The work done is Fx dx, x initial to x final. Okay. Again, this is still a straight line path. Yep. And now if you have a general trajectory, work done is this line integral. Okay. So now you have know how to calculate the work done in all cases. Okay. Now, once you have calculated the work done in all cases, what have you done? You have calculated how much energy is being transferred from one object to another. Okay. Do you guys understand that? Okay. Yep. So dr is the displacement from here to there. And that's a three-dimensional vector. Okay. So now you can be flying, and the small displacement is dr. Okay. If you're moving along a straight line, we didn't want dr, we just wanted dx because you're moving in only one dimension. Okay. All right. Now here's the work energy theorem. So it's an important theorem. Now we'll prove it in a very specific case, very special case, but the theorem is true in general. Okay, so here's an object, and we have three forces acting on it. So here's the weight of the object, here's the normal force, and here you're pushing on the object. There's no friction. The normal force is canceling the weight. So essentially, this is the only force, net force acting on the object. Okay, so if you, by the way, so if you have several forces acting on it, the net work done is the work done by all these forces added together. Okay, you can calculate the work done by each one of them, and that's the work done. Okay, in this case, since the displacement is in this direction, how much work does this guy do? The displacement is in this direction. How much work does this guy do? None. Why?
Because not the direction of the work done.
Because the angle that vector makes is 90 degrees. Okay. How much work does this guy do? 0, again, because the angle is 90 degrees. Only this guy does work. Okay. So we are talking about a very special case. Okay. All right, so this is the only guy that does work. So the net work done is the work done by that force. Again, that force is in the x direction, so there's the force. What does the force do? It gives the object an acceleration, and mass times the acceleration is that force, dv. Okay. Now we'll do the following trick. What we're going to do is we're going to try and integrate this. Okay. So we are going to use the chain rule. Okay, so what this is saying is, okay, so this is taking the derivative of the velocity of the object as a function of time. Now let's say we had the velocity as a function of position. So you take, so what we are saying is x of t. So this is giving you velocity as a function of position, which is a function of time. Okay, so this dv by dt would be equal to dv dx by dt. Okay, so this is using your chain rule. Okay, and so this would be dv by dx times dx by dt times dx, and now you can dx by dt is v, this is v, and you can cancel this x, loosely speaking. Okay, so this integral becomes m dv dv, and this is v, so mv dv. Okay, so essentially this is a change of variables. Okay, so instead of integrating over x, now you're integrating over v. Okay, so that's what happened. And now this integral is easy to do. You guys all know how to do this integral. This is x squared by 2. Just like that. Integral of v dv is v squared by 2. Okay. So this is mv squared by 2. And then you're applying at the initial and final point. Okay. So the work done is equal to 1/2 mv squared minus 1/2 v initial squared. Okay, so let's look at this. Let's stare at this. Okay, so if you add up the work done by all the forces, here's the statement. The net work done shows up as change in kinetic energy of the object. If you do positive work, you're increasing the kinetic energy. If you do negative work, you're decreasing the kinetic energy. And if you do zero work, the kinetic energy does not change. Okay, so when you're applying brakes, your bleeding energy, your final kinetic energy is less than your initial kinetic energy. Okay. When you do positive work, when you're accelerating, okay, your kinetic energy is increasing. And when you're cruising, the work done by the engine is being negated by the work done by friction force. Okay, so the net work done is 0. Okay, so this is the work kinetic energy theorem. So you need to be familiar with this concept. Okay, so W is work. To do work, what do you need? I'm sorry? You need energy. So power is the work done divided by the time over which it's done. So it's the rate at which work is done. It's also the rate at which energy is consumed. Okay? Work is measured in joules. Time is measured in seconds. Okay? So the units of power are joules per second. And this combination of units is called a watt, after Mr. Watt. Yep. Now here's another commonly used unit of power, 1 horsepower. 1 horsepower is 746 watts. Okay. So, do you guys know why it's called a horsepower? Okay. Huh?
Vaguely.
Go ahead.
I can't remember the name of the observer who discovered it, but he was originally going off of ponies pulling coal
Right.
out of mines.
So this is what this is this is the average rate at which a average horse can work for 8 hours. Okay, and that's called a horsepower. A human, if you want, a human can work for 8 hours at the rate of 1 horsepower, 0.1 horsepower. Okay, so a horse can do the work of 10 humans. Okay, so now you know why they use them in agriculture and stuff. Now, does anybody drive a powerful car here? Anybody? Okay, so, oh, you don't want to admit it? All right. What's that? Yeah. All right, so now you know what a 300 horsepower car means. What does that mean? It's like 300 horses attached to your car and pulling. All right. In the old days, they had 2 horses pulling a chariot. You had 300 horses pulling your chariot. Okay?
3,000.
Yep, that's right. That's a powerful car. All right, so anyway, so power is rate at which work is done. Okay? So power is dW by dt. What this is this is the total amount of work done after that time, and you take the rate of change of dW by dt is the power. Work done is F dot R. We're just giving you a special formula. Okay, and if F is constant, it's not changing with time, you can pull that out. Okay, and so F will come out and it'll be F dotted with dr by dt. Dr by dt is the velocity. So power can be calculated like so as well. Okay, it's force dotted with velocity for constant forces. Okay, so that gives you the instantaneous power. Okay, here are some numbers that we talked about. Yep. All right, so we are almost coming to the end of the chapter. Okay, so here's, so 2 horsepower is of course 1500 watts. Okay, maximum power output for humans for various time periods. Okay, so a strong human, you can work at the rate of 2 horses, but you would be shot in 6 seconds. You want to work an 8-hour day, you can work at the rate of 1/10 of a horse. Here's an interesting number. You can work at the rate of 1/3 of a horse, 250 watts, and you can last about 35 minutes. Okay, so 35 minutes, that's how long it takes me to run a 5K. How fast do you run a 5K? 16 minutes? Okay. So here's an interesting number. So this is a third of a horse. You can last 35 minutes. This guy flew across the English Channel, and he's working at a third of a horsepower for 3 hours. Maybe he worked like that because he was afraid of the sharks. No, that's a super athlete. Yep.
What's the wattage for like a Tour de France rider?
I don't know the wattage, but I understand. Okay, this is what I remember. So what's my normal calorie intake is 2,000 calories a day. They're eating, when they're racing, they're eating 12,000 calories. So I'm 100 watt, so that's 1,000 watts.
And they're riding for hours.
That's right. Well, so it can't be 1,000 watts because they're, let's say, even if they're riding 6 hours, that's a fourth of a day and stuff like that. So maybe they're roughly that for 4 or 5 hours, 5 hours. Better than this guy. All right. All right, we'll talk about some stuff that you need to be aware of as a young person. Yeah. So here are various values of power. Okay. This is rough number. This is a gigawatt. A billion watts is a gigawatt. Okay. A Hoover Dam is roughly 1.3, 1.5 gigawatt. We'll say 1 gigawatt. This is a large power plant, and you can run 1 million homes in the US. Okay. Actually, you need sort of 1.5 gigawatts, but we'll talk rough numbers. Okay. So this is what you want to remember. Okay. By the way, let me show some other numbers. So your refrigerator and your air conditioning are the biggest hogs. So your refrigerator is about 600 watts. Okay. A resting person is 100 watts. Okay, so you all are glowing like a 100-watt bulb. Okay. That's the energy you're using, and so that's why you need 2,000 calories to maintain that. Okay. 20% is used by your brain. Okay. All right. Now, before we get to those numbers, talk about that, let's introduce a kilowatt hour. Okay, so power is work over time or energy over time. So energy is power times time. Okay, a watt is a unit of power. A kilowatt is just 1,000 watts. So this is power, unit of power, times time. Power times time, this is a unit of energy. You guys understand? Okay. So 1 kilowatt hour, that's 1,000 watts, and 1 hour is that many seconds. A watt is joules per second. Okay. So this is equal to 10 to the power 3 joules per second times 3,600 seconds. Okay. The second cancels. So this is roughly 4 million joules. Okay, so this is the unit that's used by the electric company. This is what you pay. For this, you pay about 12 cents in your electric bill. Yeah, per kilowatt hour. So that's a useful unit of energy. Okay. All right, any questions before we start some fun slides that I think you guys should be aware of. So that's all the important stuff. All right, I'm going to quickly go over some of the other slides. Do you guys have any questions at this point? All right, so what I'm going to do is